Welcome everyone for Cloud Computing and Big Data. Today we have our short lecture 5, Deep Learning Driven by Big Data. And we start now with a series of short lectures because we basically have used lots of material already for the industry project with Ingolfur. We have seen the invited lecture series from Andreas Lintermann that I heard was very good in your opinion, and everybody liked the material, and many of the materials we would have in the consecutive lectures now will basically introduce similar things. That's why we can shorten a little bit to avoid repetition in the course. So the short lecture 5 will be basically just one course hour, and hence we have today also short lecture 6. But before we dive into the material of short lecture 5, let us review what we had the last time. And the last time was really a short introduction again into virtualization, which in the most eyes of computer scientists and computer engineers should rather be the lecture of 101 computer science today. So essentially, virtualization is a basic technology today that we will use and of course scale up. But if you recall a little bit what the traditional computer is looking like with lots of hardware, is a similar things with your laptop. You have the hardware directly accessible from the host operating system and several different applications running there. And the virtualization changes this a little bit in introducing this so-called virtualization layer. Some of you know that from hypervisors or virtual machine manager, there are different terms for it. But basically, you have VMware and other, players that provide products that then abstract from the real hardware underneath and create so-called virtualized hardware, right, that you see here. And this is something then where guest operating systems, that could be Windows, could be Linux derivative of some kind, can host different types of applications using the concept of so-called virtual machines. The virtual machines come back to us today. So we will learn how deep learning can be used in virtual machines. And we will do this in cloud computing on scale. And this brings us also already to the next topic where we said here in lecture 4, okay, virtualization to the rescue. But how does it look like if you have a large data center and you want to maybe have some Spark workloads that we already know from our initial lectures run on it? In many ways, you see this a little bit abstracted here, is that you have this physical cluster that's always something what you need, lots of racks, right? And you have seen a little bit how the construction of the data center looks like in the last lecture. But you see that the physical cluster with all the racks, be it even in different, let's say, physical locations, even maybe, somewhere differently in the US, several different regions, or you basically have here one which models all the racks. So the concept still is that you have this virtual cluster spanning then these different physical clusters, and have different virtual clusters instantiated on this physical clusters. Of course, depending on your availability of capacity. You see here's basically maybe room for another type of virtual cluster 2, but there's no place anymore for virtual cluster 4. Right, and this is of course something which alludes to some of the challenges if you scale up with different users, multi-tenant, multi-user environments. You have to schedule jobs, you have to schedule the cluster capacity. And this brought us very early on also in the last course to the concept of resource sharing, which is of course there then much more easier having this virtualization concept, because now you don't have to give it, say, for the green user group physical cluster 1 or for the red one physical cluster 2. You can basically, based on the applications and services you have, schedule this. And, then ending up perhaps that the green ones here get some part of this virtual cluster 4, and the red team, which is overlapping with some of the user, get virtual cluster 3. So in this, you have a much better control, much better flexible resource sharing if you want, which then, if you remember from the last time, was really the first idea then of getting to this cloud computing. So there was grid computing in the past where, you had also services, but not really over the internet, also not really so scalable in the end as it is today. So realizing this idea of economics of scale, large data centers and so on, and really using different data centers in different regions and so on to fuel, let's say, AWS, the Google data centers and so on. So in the end, you have also many benefits apart from resource sharing. One of it is here the live migration in terms of errors. right? Let's say that some hardware is overheated somewhere here in the rack. So what you can do with these virtual machines and with the general concept of virtualization is very quickly migrate the application to another hardware that is still running, and with this reduce the downtime of the services that you offer here in the cloud. When you have a real implementation view, you see that this is of course an idealized picture, right? That's what the user sees. If you're really, more into the backbone and see how the cloud is really working, you see lots of different physical hardware. As I said, that's always what we need. That's why I also promised you we will visit one data center together. And then you have a virtualized platform on top, which essentially then abstracts the hardware, gives the platform then to different, let's say, virtual solutions. And here you have the whole virtual infrastructure now that you see a little bit here alluding to as different virtual clusters. And you have lots of different services that you already need in order to manage this, right? Load management, resource provisioning, scheduling, security, very important as well. And the whole infrastructure system services, which then goes even into billing, and having user management, meaning you want to have some users, added or removed over time, revoke access, grant access. So there's lots of infrastructure services needed to realize the cloud that you see today. So in many ways, this was really then a quick summary of virtualization and then with data centers. And today we will go to the short lecture Deep Learning, which directly gives me a disclaimer that the short lecture is, of course, something which you can imagine that a complete introduction to deep learning needs a complete course, right? Or at least substantial training courses. We have a deep learning course in the university. So this is by no means a whole machine learning, deep learning course part. The point of this lecture is to connect what, Dr. Andreas Lintermann has put, in there in his slides, a bit conceptually in his invited lectures, and now put it a bit practically into cloud offerings. So we will revisit artificial neural networks. We will revisit deep learning networks, particularly convolutional neural networks, and we'll put that into the idea of the handwritten character recognition, a very, let's say, benchmark idea of having machine learning data sets analyzed for classification of digits. And then we basically see how that can be done in the cloud also then in short lecture 6. So with this, let's start. And one thing I wanted to convey with this is the increasing computing complexity. So you will notice that when we come to deep learning, there's an amazing computing complexity that we basically leave the realm of CPUs. And that is something you also should learn by this lecture as an orthogonal endeavor, not only cloud computing basically and their solutions and how basically deep learning works and maybe artificial neural networks works. Also the idea is that this growing trainable parameters that we will explore together now is really the computing complexity, why we need HPC, why we need cloud computing. So connecting to a little bit what we had also in our lecture, basically 2, 3, and so on with machine learning. Remember, we had the basic, simple linear perceptron model. Linear because linearity in weights you see here. So that means we have, let's say, a very simple model where we have a certain activation function, where we have our basically data set going in. And, we sum them up linearly using weights. And this weights is then the trainable weights, right? So we'll have an emphasis today on looking on this, how this is actually increasing when you have a typical perceptron, but we will extend to, multi-class perceptron, but then go quickly to artificial neural networks with an explosion in trainable weight parameters, and then even go to deep learning where this is enormously. So in a way, that's a simple model for the data set. We have the handwritten character recognition MNIST. Maybe some of you are familiar with this. The idea is here that you basically have a 28 by 28 pixel of handwritten character, and you would understand or would like to understand, is this, one of the digits 0 till 9, so 10 different digits. It's now a 10 class classification problem. And this extends our idea of having binary classification we had before to now multi-class, right? Classification, saying 10 class classification problems. This data set is quite handy. It's sort of a benchmark, very much not big data, as you can see, but it makes a point of having a training set and test set again. And it's nicely convenable, accessible also via Keras, already one of the, let's say, deep learning frameworks, and it's widely known to be always, let's say, used in training and teaching. So when we want to look at this, we want to look a little bit how that looks like in the data set. You remember the CRISP-DM in the beginning, data understanding first. Now that we have the business understanding of do the 10 class classification, we have to understand how the data set really looks like. Handwritten characters, okay. So we look here that basically you have the different, let's say, gray values of the characters encoded here. And the beauty is when we look in the data set, we come back to our point that it's actually a supervised learning problem, right? So you see here, someone labeled this as a 5, someone labeled this as a 0, and so on and so on. So for us, that means it's a little bit easier to do supervised classification than perhaps doing other measures. That's very good. And the other part is what we want to connect to is that we have, of course, the idea of a training set, a test set, right? And this is already nicely given. If I come back to the last slide, we have around 60,000 for training, 10,000 for test. And this is a very nice beauty idea to learn from. So also there we are on the safe side in the data understanding, but there's more to explore. Particularly when we want to use now, let's say, concrete frameworks. And I think Andy already made a point with several deep learning frameworks, and I will not repeat again and again here on the slides what he was presenting. So I would like just to point to you that there are different frameworks. PyTorch is another one. TensorFlow is often used in teaching combined with Keras, because Keras carries like a very nice idea of layered way of looking at deep learning, exactly how you would, let's say, visualizes. That's why it's a bit more easy accessible for, let's say, users or beginners of deep learning and so on. So by using these tools, they are basically available in the cloud. And the way how we look at this is to look at the so-called Amazon machine images. And this is something where I just pick AWS right now, right? So there's Google providing you with a similar set. You have seen in HD Insight, there are already virtualization solutions. So basically what you see here is just one example how to do it in the Amazon Web Services Cloud. When you go there and you have the Amazon machine images, it directly reminds you to the idea we had in lecture 4 before, right? So virtualization to the rescue. These are basically virtual machine images where you have already lots of software installed, which is a big benefit, right? When we just explore the one here that you see in the Amazon Linux way with the different operating systems here, you see deep learning AMI, right? And you see here TensorFlow, the packages I was alluding to in different versions, PyTorch, another deep learning package, Neuron and others. But you see also nicely, the underlying libraries to work with NVIDIA GPUs like CUDA, for instance, or cuDNN and Nickel. These are all required to have a high performance, let's say, GPU computing done if you want to use, deep learning on GPUs. And we will explore that we really need to do this. Hence, deep learning is at large very nicely supported in many different ways in AWS, in Google Cloud, in HD Insight, using virtualization, which is sort of in the infrastructure as a service level. Some would say also in the platform as a service level, perhaps. But there are also other services we will explore later in lecture 6, for instance, where we use an AWS SageMaker, which is actually on a much more higher level, right, on the SaaS level. So we will explore with this also these different levels and come back after lecture 7, 8, 9, 10 to also explore more on these service offerings or these levels. But this is now very nice. So we know essentially we have a cloud computing service. I can swipe my credit card. I use the Amazon AMI. So we are there on the safe side. So, but how it is with our, data problem. And again, CRISP-DM to the rescue. We looked before in the data understanding, so we really looked with some Python code now into the data set. We can nicely print that out as we have done before with the gray values, right? And see that here with a couple of lines, loading it nicely already with a training and test set available. But we see also quite some interesting point to it when we now realize how our modeling is, right? We want to start with a perceptron learning model. That's what we know. But what we know is that the perceptron learning model had just a one-dimensional input. one vector, right? How do I do this when I have two-dimensional data sets? Hence, here's already some data preparation step from CRISP necessary to reshape the data in one long vector. Some people know that from scientific computing that is more often done, like, for instance, vectorization concepts and so on. So here, what we want to do is now to get this two-dimensional input into a very long vector so that I can still use my perceptron model. For some of the more advanced people in machine learning, you will immediately realize by doing this all in one vector, we lose information. If I would be now in class, I would ask you what information. And you can clearly see that when you put all in one long vector this way or that way, you usually will lose some of the neighborhood of these gray values, right? So basically the 5 will be stretched across a long vector instead of a two-dimensional input where the neighborhood tells you a little bit about if it's still gray or white. This will be a key theme when we come later back to deep learning. So I want you to have this in your mind. You see that also a bit here. Basically this is now the long vector I was talking about. We require to work with a model. We got fixed on the perceptron model, and that's why we basically move later to other models. But that's what we want to start with also to compare some accuracy. Can we have better models? What is the computing complexity and all of that? So here we do nothing else than have one long vector now generated out of this. And now it actually fits with, the input, which is now, one long vector. And, 28 by 28 is 784 here, the input. But you will also notice that when we had the old, let's say, perceptron model, it was binary classification. So we had a sign function here that was determined and saying +1 or -1 in the example of flowers, for instance. Now, what we need is sort of a multi-class, 10-class problem that we can nicely, add here with a dense layer, fully basically connected. But essentially you connect it directly with the input. So it's not yet an artificial neural network, right? There's no hidden layer if you want, like, what Andy was saying from the artificial neural networks. So what we do here, we give the input of reshaped, the long vector, and we have a, let's say, dense, fully connected layer directly with the sequential input. So in the end, it's just the input with the output together, but in a dense fashion. Hence we have, this times 10 for the bias, and then also, basically +10 for the bias, but then times 10 for the different, neurons that we want to put in now. So we have already quite some weights to train on here. And this will be important for the trainable parameters because we have now around 7,850, right? So we add something called the activation softmax, which gives us an output probability, which class we're talking about. So this is a basically machine learning toolkit idea of saying this will remain for us since quite a long time, because it squashes basically this different values between an n-dimensional vector of these values that we need. And, basically it aggregates this, what you have for 10 layers. Hence, we can see which class of the 10 it would be most probably like. There's not a definitive solution, like 100%, but often 99% and so on. And the reason is that some of the digits, of course, share certain properties. You have an 8 is similar like a 0, right, in one way. If you think about how you write it, it's just not a middle, let's say, connection between the left and right and things like that. Also optimization that we had, in Andy's lecture, but also from me before, is nicely supported in the cloud with this different, different tool sets like Keras, TensorFlow, PyTorch. You have several different optimizers. Here's the SGD, stochastic gradient descent, but you basically have also Adam and others that are very popular. And they, basically have then the idea of specifying a loss function and using then this optimizer to get this loss, let's say, minimized. So here comes the minimization problem. And I'll not go again into detail of this too much. You can see that, we want to go down the error surface by taking derivatives with a certain learning rate. And the learning rate will be interesting for us later as well, because here it's where we then basically can steer a little bit with the human, the learning. When we come back to the practical idea, how we now implement this in Keras, basically you see here the number of epochs, how often we want to go essentially through the data set, how we crush the data set into different instances. Here, the batch size, 128, the number of classes, the optimizer, and then we have the same, what we had before with the data inspection and data understanding. And then now we say, this time we want to reshape the data. For mathematical convenience, we also normalize the data very often in machine learning. This means there's not only more large values, but rather smaller values that then for computing are more convenient. And then we give that just the number of training and test examples out. So then combining this with what we just said with the multi-output perceptron, we basically now start with a sequential modeling of Keras, adding this dense model with 10 classes with a reshaped input. So having the input directly connected to the output. And by doing this, we use a softmax activation function basically to get the class probabilities. And you will see later that this is still used also in cutting-edge deep learning often. So here's some of the basics. Again, I think the softmax was also already explained a lot, so I go here a bit faster. Same is for the optimizer to minimize the loss that we specify with the categorical cross entropy that you see here. This is of course something which should fit a little bit to your problem, right? So the loss function is something what you specifically choose, and here the categorical cross entropy is just very good for this multi-class logarithmic loss. So that's why we picked that one and not another one. Then we start with a real training, and you will find that model.fit or model.fit is often in many of the machine learning packages, the function where it starts really getting interesting. Here's where also the computational time suddenly increases. So we need the training set, we have the batch size, how much I, always update essentially my model on depending on the batch size I'm walking through, then the epochs, how many times I go through the whole data set, and verboses for the output. And then I can evaluate the model, basically on the metrics we have, like for instance, accuracy here, and then can see the test score and the test accuracy that we are interested in. So basically, how well was our multi-output perceptron model working? Now, then you see that now in running this in the cloud, maybe using Jupyter notebooks, we come to this also more and more. You can run it as a simple Python script also with the AMI interface that we have seen with the AMI machine learning, virtualization layer in essentially AWS, but also in others. Do you see how that works? We can see that the accuracy is quite high, right, of the whole code. That means the model is already quite sufficient in a way for this, let's say simple problem. But we can also, improve probably. So it's still, 92% accuracy here. And this number of epochs is also something what I wanted to talk to you about, because, in the normal machine learning course, you will quickly talk about so-called overfitting, right? Or maybe even underfitting. Underfitting means you rarely look at the data, but there's a sweet spot of saying if you, do the number of epochs too much, if you learn the data too much, you see what's happening here. You more memorize where the data points are, and the model will be very much optimized to these in-sample performance, or what we have in-sample in the data set. And then when there's a new data, it will be a large error. Now, when you underfit, then it's a similar idea. So you all basically have a model that is not really trained, that looked at the data. So what you want to strive for is a so-called optimum in a way, which you see here. And that's why you have the test set, hopefully tracking the training set. And that's why we never use the test set in training for really evaluate what's happening. And you can see that quite nicely, that even if you do 2000 epochs, you will get the training down and the error down. But there's a certain sweet spot here where it starts with overfitting. That means if you use an unseen data which is not these points, but new ones like this one in the test set, then you will see it follows nicely suit. But there will be the sweet spot where it starts to increase significantly in error again. A concept we called overfitting, and regularization and validation is basically, there's two concepts in the machine learning course to combat overfitting. Hence, we cannot do this here in a small course like, this cloud computing course, which has many other ideas, what we want to teach alongside. But for you as a practical consideration for real practical problems, please make sure that you have always regularization validation adhered to, and that you have always a training set and test set, separate from each other. Ideally, also multiple validation sets if you have the data. Now, when we review this now, where we are, we have 92%. Now we have actually learned a little bit more with more epochs, maybe, and coming up to 91%. So this is a stochastic, process, the optimization. So we never have necessarily the same, but they're in the same order of magnitude, right? With this particular model. What can we do now? And I mean, with you having the brilliant lecture from Andy, you know by now what we can do. We can introduce hidden layers, maybe one or two. We can change essentially the activation functions in front of these layers or in these layers if you want with all these different neurons. So what happens if we change a little bit? And this brings us to the domain, which also I think Andy was alluding to, the non-linearities, right? The problem of the perceptron linear learning model is, the linearity. You see that XOR problem, which is very famous, would be one of the classification problems it can never solve, right? So if the perceptron learning algorithm will never stop because one is always misclassified. You cannot put them on one line on the other, right? I think the graphic shows this nicely. However, and that was now sort of the breakthrough, if you want, for the artificial neural networks that we will have soon, you can do something called multi-layer perceptron. So the idea of a perceptron, which we had very early in the course, remains, but you add them up. And you have basically connections. These are also trainable weights, which you then take on input from the previous layers, introducing essentially a hidden layer. Right, and you can have many hidden layers, and you can have many different neurons, as you learned from Andy. So hence, this is a start where you think about now having much more interesting decision boundaries, or decision spaces, if you want. You see that here. Linear activation functions produce linear decisions and will not catch the data very well. With the non-linearities that you now put in front, or basically alongside all the hidden layers, with the activation functions that Andy was also introducing you to before, rectified linear unit, very popular, the leaky ReLU as well. So basically with this, you have now the power to choose what basically you want to put in front of the perceptron that we have still in a way realized with all the inputs, but they coming from the different layers beforehand. So hence it looks like that. And I think this also is a repetition basically of what Andy was saying, that you have always this forward pass through the data. That is what you can nicely compute. You will initialize the weights of some kind. You compute the error, but in the end, you would still have a softmax to understand essentially what is the probability now of the 10 classes, which class is a winner. Given you have a supervised learning problem with your class given, you basically can very quickly evaluate, is that the right class? If not, you start something called backpropagation of error, using the chain rule, things like also Andy was discussing, updating the weights through all of these trainable parameters. And this alludes again to the point. Right now you have the weight update phase. These are all trainable parameters. And we have seen that before. We compute the gradients, and this is now where the computing comes in, right? That's where it's now starting to be computing intensive. Taking derivatives, taking the gradients of all these different connections you have seen, right, throughout a big neural network can take actually quite sort of time. So, and then you want to update the weight vector, and then of course you do another forward pass and see if the error is good or bad, go back. So you will come back to this loss function idea that you also see here. You go down the error hill until you hopefully land in a global minima of error, and will basically say, we have learned the best way we can. Maybe not everything perfectly. Here's the learning rate issue in this. When you say that the global minimum would be here, and the learning rate can help you a little bit, where you say when the learning rate is, let's say, too small, you end up in a so-called local minima, somewhere here, perhaps. And when you have the learning rate too tough, when you basically do this error and, the learning rate that you have here too much, then you're jumping a lot with the weight updates, right? Hence, you will also miss the basically global minima. So again, it's a sweet spot in a way to have the stable learning rate coming then over time, as this graphic suggests, to the minimum of error, and then reports the best, let's say, weights that you have to compare to the loss function to, have best learned in a way. And that's why we do learning. If you remember in lecture 3, I had also the nice overview that the error measure is basically your helper in learning to pick the final, basically hypothesis G. Now, let's do this in practice with Keras if you want, basically here. And of course, you can see also in the course we had last year in YouTube, there are extended versions of these lectures. So if you want to see also demonstrations of this in practical lecture 7.1, you can look to lecture 6 and 7. There's much more material. I left that a bit out because Andy essentially covered many of these things already. But here and there, we have also, let's say, spent lots of time in the industry project, right? So we have to continue with this as well. However, it is very similar, the batch sizes, number of epochs. We have now only the new parameter number of hidden neurons in the hidden layer, right, that we want to do. And let's assume we want to do 2 hidden layers. That's what I do here in Keras quite nicely. Instead of having, basically the sequential input layer directly to the dense output layer, I connect it now in a dense fashion to the hidden layers with a reshaped input that we know from the characters, and have an activation function rectified linear units to basically then have this nonlinearity. And then I do this twice and connect it again to the, dense at the end and add my typical softmax to understand the probabilities. So this is still there, basically. Now, when I run this, no surprise a bit, it's a much more, let's say, powerful model. The neural network is maybe one of the most powerful models that you have. You can basically see we increase the performance of accuracy to 97%. But what does it mean for computing? And, when you do this again, maybe with some regularization, you come to a value which is 95%. So it doesn't matter, again, stochastic, processes never maybe have directly the same, but it's again in the same number of, values compared especially to the multi-output perceptron. So we have already 95% performance with 20 epochs, but we had to pay the price for it, right? This is what you see here. The total number of parameters suddenly from 7,800 was actually massively increasing with the weights here, right, to 118,000 roughly. And you see that a little bit here with the parameters on each of the layers, but this is where the computational complexity now comes in. That's why for larger neural networks, we really need GPUs. We really need more computing. And when we go now one step further, going to deep learning as promised, we will see an explosion of these parameters. And we will see why by just, basically coming back to one of the simplest deep learning models, the convolutional networks. Also here, a complete introduction is given in last year lecture 6 and 7. Andy touched on it, and some actually use it already in the industry project. So here we have the idea that we have still this classification layer with softmax at the end. But instead of doing just hidden layer by hidden layer, if you remember one of the earlier course hours, I said deep learning is not just this. You have specific layers, which are basically doing convolution operations, going through the pixel image. And now the interesting thing is it keeps the 2D, right? So we don't lose information as a vectorization with a reshape. If you remember from the first modeling, there will be still maybe some samples that you see here that we can't catch, right? It's very hard to determine what actually the real author of these characters wanted to have. But still, these are very powerful models that are doing basically feature extraction in a 2D way on pictures, essentially, right? Hence, it's very good for image recognition. And you go systematically through it with a so-called convolutional filter. And that's the thing that you learn then. Now you have this filter matrix of weights. So there will be lots of trainable weights with this, going through each of the different layers. And you see how that works a bit with a convoluted feature. Then it multiplies. In the end, it stays with matrix multiplication, matrix vector multiplication. But the point here now is that you have lots of weights to train. Now, the nice thing is that with this, you can carve out features. That is a little bit explained in the idea of here with the car, where we have different feature maps, maybe, recognizing rather the tires of a car or the front with 2 lights of a car. So these are things which are then taken by these feature maps that you learn, or basically then we will see in the numbers a very similar way. At the end, you flatten all of this, what you do consecutively over many different layers. There's also the pooling layer that is then, let's say, sample out, more the number that you have and come to a smaller set, in the end to have more smaller features in the data set recognized. But the whole idea is to identify features, right? Hence we call that feature learning. And then you do the standard classification that you already know from the multi-output perceptron or from the artificial neural network. So there's nothing different. The only thing we change now is that we have someone thinking about features, feature learning, what's in the data. And I brought you here this example to play around with. So I would encourage you to use this reference and play with this. It's an interesting, nice interactive demo where you can do this writing of your handwritten character as well, and then go through all the layers and see how these feature maps are going, and basically also in the lower layers, and then recognizing a 7 at the very end, right? If you think about the softmax probability, this is highly likely a 7. If you do this and then do 8 or 9, you will see that some of the lines are overlapping, so the probability is not so 100% certain anymore. Also here it might be actually just 99 something percent. So interesting tool to learn from. But for us in the lecture, we want to go on a bit and understand now what was the price I pay and what the kind of Keras basically Keras source code looks like. So we have an interesting idea again of sequential model, but now we add what we had seen here in the overview. So we add a couple of convolutional 2D layers. So we look at the problem in 2D with a certain kernel size. So how big should my feature map be and how much is the kernel matrix we go over. And padding just means how I will actually end up with the ends. So if there's not 5 anymore, do I pad some, values for it or not? And then, to do some pooling to strengthen the signal here in a 2x2 fashion. And then you do the same thing with maybe 50 feature maps, thinking about the smaller we've crunched down the problem, there may be more features we find, from the different handwritten characters. Then we already flattened the whole thing in order to put it into a dense layer, if then we have a low vectorized input again, and then I'll do our softmax probabilistic, output at the end. And then you can, build this model that we have essentially, in this function here, and compile it and then run it, and basically you will see it here with a number of parameters really exploding. And I think things like that connects nicely what Andreas was saying. This is where the computing now is really required. This is where parallel computing quickly comes in. This is maybe just manageable on a GPU because it's a toy application problem with the handwritten character recognition. But if you have then really applications that Andy was alluding to in engineering, fluid dynamics, whatever, then you have quickly much more layers. You have much more, let's say, neurons in each layer. And then that means the trainable parameters really exploding. We see here an increase again from the 7,800 we had with the perceptron model, and then to the couple of thousands we had then in the artificial neural networks. Now we have 1.2 million for a toy problem. But of course, this helps us in a way. So we will see the accuracy is definitely better. And what I have to do for it is a little bit, similar that the things you already know. We introduce also a bit of validation splits here, which I want to put to a later lecture. So validation, cross-validation is something where we need, again, HPC quite nicely. And we will do this in a hyperparameter lecture at the end of the course. So not to do too much here today. And in a sense, the code is very similar, right? We basically normalize the code, but you will see we don't reshape anymore. We have a 2D input data, which is now important for you. And for the deep learning network, it maybe makes sense to have ADAM, which is a bit more with the adaptive learning rates, a quite nicer idea of how to learn from. And then you see what we get out of this computing complexity nicely. We have now 99.3%. This varies a bit. You will never reach 100% because of this, right? Even for the human, some of these more in the data sets are not recognizable. And this is a typical machine learning point. You have very rarely in production really completely 100%, and usually 99% is also very idealized. Hence, this is alluding to, again, that it's essentially a very simple problem to solve, right? It's much different when we go remote sensing with satellite data sets, multispectral, hyperspectral data sets, different bands, and so on. And this captures the essence I wanted to talk about today. Let us summarize a bit. You can do this very nicely if you do this, with Jupyter Notebooks, for instance. Use the code you have seen here, upload it, and the code will be available to you. It will be not an assignment, so it's optional for you to try out. But we have this larger hackathon coming up where maybe some of the things you already will do similar fashion with screws and LSTMs and so on. So this time we don't have time in the course for doing this with CNNs, but the code will be available to you to use. And finally, what I wanted to say is also this overfitting, right? Again, I'm doing here a lot of machine learning, deep learning, but there's lots of machine learning fundamentals you have to understand if you want to go, in industry doing real projects. One of it is really overfitting, maybe the most important principle if you want to understand, because this will report wrong accuracies. And you see a nice video that shows it a bit. With 3 hidden neurons, you cannot do much. With 6 hidden neurons, the model complexity might be just right. But if you do 20 hidden neurons, so also that means to you, it is not necessarily always a training time. It's also the model complexity that might be, too much. And you see here in the 20 hidden neurons, it's quite actually memorizes the data instead of creating some form of a decision boundary. So I leave it at there, and we will talk about, short lecture 6 in a moment. So let's have a short break.